Welcome to the lecture number 3 for blockchain technology and applications. So, what we will do today is announce a homework. It will not be graded, but it is something that you could do yourself, so that you can actually familiarize yourself with a number of concepts that are very important in blockchain. So, you will be designing your own blockchain platform implementation. This is going to be a little bit simple blockchain application. So, it is not really how the Bitcoin or Ethereum or other blockchains work, but it will have the concepts that will allow you to understand the other blockchains better. Now, if you do not know C++, then this homework may not be something you could do unless you actually learned how to program in C++, at least the minimal concepts and the data structures. But even if you do not know C++, the concepts still are pretty general and you should be able to understand those. So, the material for this lecture and the exercise was created by my colleague Professor Pramod Subramaniam from IIT Kanpur. So, we should acknowledge his help in creating this exercise. So, the question is how to create your own blockchain. So, what we will do in this lecture is we will build a ledger of transactions, and once you build a ledger of transactions, you have to make sure that I can or anyone can verify that it is a valid, the transactions are valid, and therefore, the blockchain has everything valid, and also the how to make this thing permanent, that is how to ensure that nobody can tamper with data once it is put in the blockchain. And then we will explain the first programming exercise is for your self learning. So, we will not grade them. If you do not know C++, you may not be able to do this. However, the concepts are very important. So, you should pay attention to what we are doing. Maybe you will have a little difficulty understanding how we are using pointers and various kinds of data structures, but you can probably guess what we are doing, and that will be enough to understand. So, the question is, what is a ledger, right? So, a ledger could be many things, but let us look at this. So, let us say this is a bank's balance sheet, and here we have 4 account holders and they have their balances. The question is this balance table a ledger? The answer is not really, because it is a balance table. So, it does not remember the transactions, it only remembers after a transaction what the new balance is for each of the users who are part of that transaction. But we want to remember all transactions, and we want to make sure all transactions are made by legitimate people, and we want to also make sure that the transaction actually is a valid transaction. So, now if we instead keep a record of transactions. So, you see here that we have a record of transactions. So, when Alice opens her account, she makes an initial deposit of amount 100, Bob makes an initial deposit of 200, Carol makes an initial deposit of 300, and Dan makes initial deposit of 400. So, initial deposit is one of the transactions. So, it has to be put in the ledger. Suppose now real transactions starts happening. So, let us say Bob now for some reason maybe Alice sold something to Bob, and Bob makes a transaction maybe over the internet or by a check, and Bob gives Alice 100 amount, and when that happens, then earlier Alice used to have 200, now the Alice's account should be debited to become 200, because Bob is now giving money to Alice. So, at this point Alice also now gives some money to Carol, and in the amount of 125. So, we have 2 new transactions where after the initial transactions, initial deposit transactions, this is when Bob gives Alice 100 let us say bitcoins, and Alice gives Carol 125 Bitcoin transactions, and so on. So, as the transactions come in, we want to add them to the ledger, and the ledger is always appended, nothing we do not normally want to, we do not go back to previous transactions and make any changes to them. So, it is an append only ledger, right, and we want to ensure that this append only property is enforced and nobody can go and change the previous transactions once they have been committed. And then I can construct the account balances by going through the transactions. So, earlier we started with an account balance table, but what we are showing here is that if you keep track of all the transactions, that is enough, because at any point in time you can actually reconstruct that table of account balances. So, I can actually see that Alice initially deposited 100, then she got from Bob another 100, then she gave 125 to Carol. So, her final balance at the end of this transaction is going to be 75, whereas here if you see Bob, he has given 100 to Alice, and initially he had 200. So, now he has 100. Carol actually got money first by initially depositing herself 300 plus 125 here. So, she has now 425, and Dan did not get any money or give any money to anybody. So, his balance stands at 400. So, this balance table can always be reconstructed from the ledger of transactions. So, ledger of transactions is very fundamental, whereas from the balance table you cannot reconstruct the transactions. So, it is better to keep the transactions in the ledger than the account balance, because account balance is going to lose information. Now, when I try to do a transaction, so we spoke about that in the earlier lectures, that not all transactions are valid. For example, suppose at this point Bob wants to give Dan 200, but Bob has an amount of 100 after all the transactions he has made earlier. So, if he tries to give 200 to somebody like Dan, then that transaction will not be valid, because he does not have 200 at this point. So, therefore, this transaction will be rejected or should be rejected by the whoever is keeping track of validity of transaction. So, in case of a bank, the bank keeps track of the validity of the transaction, but in a blockchain we will see that such attempt to make invalid transactions will be checked by everybody who is part of the blockchain, or whoever is a part of the blockchain and is interested in validating transaction. And why would I be interested in validating other people's transaction? Because I want to be part of the mining system, and so if I validate transactions and then somehow after validating transactions, if my validation results are actually kept in the blockchain and many others are validating transactions and theirs is also trying to be on the blockchain, and if mine goes through as part of the blockchain, then I get rewards, I get so many bitcoins or whatever the currency is, and therefore, I have an incentive to do the validation. This is how a decentralized kind of crowdsourced validation of all transactions can be made without a central authority like the bank to do this validation. So, definition of transaction validity is now then if the sender's balance is greater than equal to the amount that the sender is trying to send, then we say that the transaction is valid, otherwise the transaction is invalid, and we call it transaction validity definition version 1, because as you will see this is necessary, but this is not sufficient to declare a transaction to be valid. So, we will come back and redefine or add more into this definition and get version 2 of the transaction validity. And a ledger validity is that if all transactions that are recorded in the ledger, if they are all valid transactions, then we say that the ledger is valid, and this is also version 1 because it's actually based on the version 1 of transaction validity. So, that is the valid ledger definition. So, in other words, every sender has an appropriate balance to conduct every transaction. So, that is the and they have been recorded, and that is a valid ledger. Now, what happens in a blockchain is that there is some further optimization. So, if you start keeping every transaction as a separate entity in the ledger, then and there are many transactions, then the ledger grows very fast. And remember, the ledger has to become a linked list. So, you will have too many nodes in the linked list. So, what people do is that they wait for some time and bundle all the transactions that happens within that time, check their validity and make a block. So, and then if these blocks are connected as nodes in a linked list. So, therefore, now how you can decide how you want to make this how much time window you have to wait until you put the transactions in a block. So, it could be on a daily basis, it could be on every 1 hour, it could be every 10 minutes, it could be some other criteria by which you decide when it is time to put all the transactions that you have seen into a block. Now, interesting part here to understand is that if bank is doing it, then it has a fixed rule that I will only wait for 1 hour, and every hour whatever transactions has happened, I will put them in a block, I will validate them, and then I will add that block into the linked list. But if it is being done by everybody independently, so there are let us say 10,000 people, each of which are looking at transactions, and these transactions as they come, at some point they have to decide now it is time for creating a block with the transactions that I have seen after validating them. Now, remember, this users or this node, this participants in the blockchain are distributed geographically. Maybe some are in the US, some are in India, some are in China, some in Africa. So, therefore, their notion of time will be varying, because the clock synchronization is not being applied here. So, therefore, what is when I think that it is 1 hour, the other participant from another place may not think it is 1 hour, maybe a few minutes here and there. Also, the other problem is that if I make a transaction in India, through the network to see that transaction happening may take more time to the US user, and a transaction happening in the US, the Indian observer may actually see them later. So, what may happen is that even if you have a standard notion of 1 hour, but the transactions you have seen at this point, by observers in US and observer in India would be little different. To reach the transaction information over the internet may be little bit delayed based on the proximity of the transaction happening and the observer. Therefore, everybody when they start creating blocks, their blocks will differ. Also, the user may say, oh, I do not like this particular transaction, so I may not include it in the block, right. So, therefore, every user, say 10,000 users are all trying to make this valid blocks of transactions. The reason they are doing it is because they will get some reward, but the blocks they create may differ from each other. So, then the question is, how do you decide, how the system decides whose block will be the next block in the linked list, and that is where the whole mining process, or the last time we talked about the hash puzzles. So, hash puzzle solving or mining process takes place, and that is how a competition starts among all the users, and this competition is won by solving the hash puzzle first, and when the hash puzzle is solved by somebody, then the person can claim that my block is the winner and this block goes into the linked list. Now, what that means is that depending on who wins, which transactions go into a block will be different. However, in this setup, in our particular programming exercise, we won't have this kind of uncertainty, because we will be doing it from one place, because it is just an illustrative example. This is not how the blockchain works in terms of creating blocks of transaction and validating blocks of transaction or adding them to the list. What we are doing here is just to get the concept of blocks and concept of linking them together, rather than completely mimicking what happens in a realistic blockchain. Therefore, for us, which transactions come into a block would be much easier to decide, and there will be only one block created, because only one entity, in which case your program, will be creating the blocks and adding them to the blockchain. But I just want to ensure that you understand that the difference between what we are doing in this program and what actually happens in the real blockchain. So, the concept of mining is absent in this exercise or in this example. Only the concept of creating blocks, validating the blocks and validating the transactions and putting them in a list is what we are going to do here, which is sufficient to understand some of the concepts, but not all the concepts. Also, as you remember, when I am doing it from one program and no other participants, I can create a real C++ linked list, right. So, we spoke about that in the previous classes, that in C++ linked list, a link between from one block to the other is actually a pointer, which is a memory address. But we also said in the previous lectures that in case of a distributed and replicated blockchain, this memory address concept is not applicable, and there we do hash pointers. Here also we will do some form of hash pointer, but that is also different from how the hash pointers are used in the real blockchain. So, those are the differences. So, we will in this case we will actually create a real C++ linked list or C linked list, just to illustrate the concept of a linked list of valid blocks, and this linking is done through memory addresses, but with a little bit of more idea thrown into it, that we will also have the hash of the previous block stored in the current block, and therefore, it becomes kind of hash pointer. So, let us see some code then. In C++, we have this notion of a class. Class is basically a structure, and this class we will call transaction underscore T, and this class is basically has 3 elements in the class, 3 data items. One is the account information of the sender, one is the account information of the receiver, and another is a 64-bit unsigned integer amount, because we are not going to deal with negative amounts in transactions, we are doing monetary transactions here. So, this is a class. Any instance of this class, that is an object created in this prototype of this class, will be kind of representing a transaction. So, every time a transaction happens, we will be considering this this kind of a information structure that will have sender information, receiver information and transaction information. So, Bob gives Carol 100 coins, right. So, that is the information that we want to put. So, that is why the class has 3 elements. Now, we have to also represent blocks. So, what is a block? Block is actually a collection of transactions, and then it has to have a pointer to link the previous block, right. So, it has 2 elements. One is a vector of transactions. So, a vector is basically kind of, you can think of, is a array of transactions, although it has lot more interesting properties than arrays, but it is a transaction. So, it is actually a list of pointers to transactions of this type, right. So, you will have a vector of transactions, which will be all the transactions that you want to put in the block, and then you have a pointer to the previous block. So, that is how the block is defined, and then the linked list then will be a list of blocks, or in this case list of pointers to the blocks. So, we keep pointers to the blocks, and the blockchain will be a list of blocks. So, that is the concept here. Now, let us look at this data structures from the standard C++ library. So, vector is actually a template. So, it can take any type T and it will create vectors of that type, and if you want to add elements to this vector, so you use this function push back, and whatever you are trying to push into the vector. So, this LM or element should be of the type whatever type T you have defined. Similarly, you can check the size of the vector with the size function. You can also access say ith element of this vector using an indexing like an array. So, vector of I equals something would put that thing into the vector's ith position. And if you want to extract the array of information inside the vector, then you can call the data function and it will give you access to the array inside the vector. Now, sometimes when you add things in the vector, so let us say initially you define the vector of a certain size and then you want to add more stuff into the vector. In that case, because you realize that initial size that you thought of is not enough, then you can call a resize function and then it will resize it to have another n number of elements in the vector. You can also clear out a vector with a clear function or delete all the elements and set the size to 0. And then finally, if you want to iterate, if you go through the list to do some action on the elements of the vector, for example, reading them or changing them or applying a function on them, then this is the new way of doing it in the C++ recent standards, that you basically say that LM is the element of a vector, and what this means is that you automatically iterate through the from vectors 0th element, first element, second element, third element, all that stuff inside this loop. So, this for loop basically allows you to go through all the elements of the vector and do something with the element. Now, the other structure that you saw, so vector was actually used to store the transactions, and then other thing that we saw is a linked list of blocks. So, list structure was used to do that. So, list has again certain manipulations. So, in case of you want to add an element to the list at the end, then you basically do a pushback function. If you want to know the size of the list, you can call the size function. You can delete all the elements of the list by clear function. You can also iterate by various methods. So, one is that you do like I equals 0, I not equals n, I plus plus kind of thing. So, here it is a pointer iteration. So, you take the first pointer and then you iterate over it and then until you reach the last pointer in the list, right. So, that is how one way of doing that. Another is doing how you were doing it on the vector. You do an auto LM vec and do something with the elements. So, for you to understand what is going on here, even if you do not know C++, you can think of the blocks. Let us look at this. So, you can think of a transaction has 3 elements, the sender, receiver and amount, and they are put, the pointer to them is put in a vector, right. So, a vector which has for first location, second location, here is another transaction, third location, here is another transaction and so on. So, this is a vector of pointers to transactions. So, each of these transactions has 3 elements. Now, is that this whole thing along with the pointer is a block, right. So, then when the next block comes, a new block is created, this pointer is set to the previous memory address of this block. So, this is how this is done. So, and then another one here, and then this is a list. So, this is the list of, so these are the pointers to the blocks, and remember this pointer and this pointer is pointing to the same thing, this pointer and this pointer is pointing to the same thing, but this is a list of pointers to blocks, and that is your linked list of blocks. So, that is how we are representing the entire blockchain. Now, another thing that the modern C++ gives you, now pointer management. So, those of you who know C++ know that pointer management is a big headache. For example, if you define a pointer and then you allocate some memory to be pointed to by that pointer, like using a malloc or a function or a new in case of C++, then your pointer is now pointing to a chunk of memory depending on what you have put here as size and everything. Now, if you stop use of this particular chunk of memory later in your program, then you are supposed to deallocate, right. So, you have to deallocate this amount of memory, otherwise your program will start running out of memory. Now, that deallocation is a lot of concern, because many times people forget to deallocate, and then we have this problem of memory leak, right. So, the memory that is allocated to be pointed to by a pointer, it has been used for a while, and then after a while it is of no use, but the programmer forgot to say dealloc or destroy or something, and therefore, the memory remains there sitting there with nobody using them. And if it happens in a lot of such pointers, for example, in a loop, then it keeps accumulating and your memory space gets gets used up, and your program then will crash. So, therefore, that is a memory leak problem. The other problem is the dangling pointer, like you have a pointer for which the memory has been deallocated, but you have in your program you start using that pointer referencing something with that pointer, and then you have a problem of null pointer exception. So, therefore, people are quite worried about using pointers. So, in modern C++, there is a smart data structure called shared pointers. Shared pointers actually are what we call reference counted pointers, which means it keeps track of whether it is under use, whether the memory allocated for it is under use or not, and based on that it deallocates automatically. As a programmer, once you created the pointer, you do not have to worry about deallocating the pointer or worry about null pointer exception, because as soon as the pointer gets out of scope or not being used, it is reallocated. So, that is why in this program shared pointers are being used. So, the only advantage here for you in the shared pointer usage is that when you allocate, you do not have to worry about deallocate. So, that is the other thing. So, it is as I said, it is a reference counted smart pointer. So, when you define a pointer, you are going to actually define it like this. So, it is a shared pointer which points to a block, in our case the block we defined, and then you have to define it like this. For deletion, you do not have to do anything, it is auto deleted when out of scope. So, that is the reason for using shared pointer, and the usage is like a pointer, right. Pointer arrow member name will give you access to that member of that structure which the pointer is pointed to. So, if the structure has 3 members, member 1, member 2, member 3, then you need to know the name of the pointer that is pointing to that, and then you reference them as member 1, member 2, member 3. So, that is the use of smart pointers, and you can also copy a pointer to another pointer to point to the same thing, and so on. So, now the question is, how do you validate a blockchain? So, what is the validated blockchain? So, you have transactions etcetera in one block, and you have next block pointing to it with transactions in them, next block pointing to it with transaction to them, and then when I say valid, I have to first check that in each of the blocks your transactions are valid, and when I say transactions are valid, I have only defined what it means for a transaction to be valid partially as version 1. So, therefore, this validation code is also version 1. So, first I go and validate all transactions in a block, and then we declare that this block is valid. Similarly, I do this for this, and then I declare this block is valid. Similarly, I do for this, and I declare this block as valid, and suppose this is the first block or the genesis block. In that case, this is not pointing to anything else. So, therefore, I declare that the entire chain is valid in the sense of the chain we have defined in this program. So, let us see how the code works. So, first of all, in this case we actually use a balances table, right. So, balances table, as I argued earlier, is that I can create the balances table from the transaction ledger, right. Now, why do I then recreate the balances table within the program? The reason is that to validate that a transaction is valid, right, I have to check whether the sender's balance is greater than the amount he or she is trying to send. So, I need to quickly calculate the balance of the sender. Now, if I have to calculate the balance of the sender every time I validate a transaction, then I will be redoing the same work again and again. I have to go through all transactions and add and subtract any transactions, any amounts that he received, and subtract the ones that he has transferred to somebody else. So, therefore, it is like a kind of like a caching technique. So, we keep a balances table on the side, and therefore, first what we do is that we create a balances table, and then what you do is that we go through the transaction and check whether there is a real sender or it is an initial deposit. If it is an initial deposit, then all you need to do is that you have to add that amount to the receiver's balance. If it is not initial deposit, which means somebody is sending money, so that the sender's balance should be greater than the transaction amount, and that transaction amount should be subtracted from the sender's balances and added to the receiver's balances. And if this transaction is neither a initial deposit or the sender's balance is greater than equal to transaction amount, then we return false. That means is that this code is for validating transactions, right. So, we are basically looking at all transactions. So, here you see that we are doing an auto BLK blockchain and auto TX block dot transactions. So, I am picking one block and I am going through all its transactions, then I am picking the next block, going through all its transaction, I am picking the next block and I am going through all its transaction, and for each transaction I am checking whether it is an initial deposit or the balance of the sender is greater than the amount. Then I do the appropriate changes in the balances and then I return false. So, in this I have one side effect, which is the balances table at this current condition of the blockchain. The blockchain is a growing structure, but at any point when the blockchain is at this stage, maybe later on there will be more here, but right now I have up to this. So, at this point if I validate, not only I validate all the transactions, but also I have constructed the balances table. So, in the beginning of this validate call, I clear out the balances if there was any other previous information, and then we start reconstructing the balances field. So, this is how this is done. Now, how are we keeping the balances table? So, what we have done is that we create a what is called a hash table, right. So, and what is a hash table? Hash table is a table which is indexed by hash. So, let us say it is a table with two columns. In one column you have some element, in the second column you have the other element, and then to access the second element, like let us say Bob this, Alice this. So, in order to know what is there for Alice, I have to index directly to Alice's name, and then I should be able to read what Alice has. So, in this case if it is a balance table, it will be Alice and her balance, it will be Bob and his balance. So, this is how the hash table is formed. So, in this case called an unordered map, and it has two different types. So, K is the type of the first element or first column, and V is the type of the second column. So, if the first column is a string and second column is a integer like Bob and his amount, then we will have integer and we will have the string and the integer. If this is a more complex structure, then let us say an address, then it will be in that structure and it will be amount. That is how we are going to define. Now, the way the map is accessed is by indexing the map with these elements. So, you can think of this kind of an array where index is used to access the elements. Here instead of array index, we can have a type K thing to index the array. So, that is the idea. So, here also again to insert something, you have to just say what key and what the element that you are inserting. The size can be obtained by this call. You can clear the map or the table to make it reset, and you can iterate through it. Like if you want to go from the first elements of the table, the first row of the table to the all the way to the end, you have to do something like this, like a pointer that begins here. These are called iterators, actually they are not really not necessarily pointers, and then you do this iteration, or you can also search by calling a find function. So, search will allow you to say okay, what is there for Alice. So, you say find Alice as a string, and then it should tell you what the amount Alice has. And also we have a set data structure or a template, C++ template. So, set, as you know, is a set of elements. So, if you want to represent it in a data structure, you have to have a way to insert an element, you have to have know the size, that is how many elements there are in the set. You can reset the set, so it does not have anything anymore, and you can iterate over the set to go from the one element to the next and so on, and you can also search in the set. So, that is the set data structure. Now, blockchain is a ledger of transactions that is verifiable and permanent. So, right now we only focused on the verifiable part, that the transactions have some validity, but permanence is something that we have to now worry about. So, one issue is that we talked about repudiation a lot in the previous lectures. So, let us say in the transaction found that Carol has given Dan 100 coins, right. Now, Carol comes back and says I never paid Dan that money. So, but why is it in your transaction? It is affecting my balance in the balance table, and so I repudiate. I do not agree that I have done this transaction. What do you do in the today's bank case? That bank comes back to you and says that look, here is the check you signed, this is your signature, we verified your signature, and therefore, you cannot repudiate. In case of an internet banking, what you do is that you say look Carol, this was done from your account, you use the signature, you use the username, password and OTP, and therefore, it is you, right. So, that is how the banks handle repudiation cases. But in case of blockchain, as I said, that blockchain is there is no central authority, right. So, you cannot just go and complain to 10,000 people who are all part of the blockchain, they are all checking validity of transactions, they are all trying to make blocks of transactions and hoping that their block makes it into the blockchain. So, there is nobody particular to listen to your repudiation. So, therefore, the system should be non-repudiable, right. So, any transaction that has been validated should be non-repudiable, and this is where digital signatures come in handy. That is when Alice says that I am paying Dan 100 coins, Alice must sign it with her private key, and then Alice's public key should be available to everybody. So, therefore, anybody who wants to check the validity of the transaction, now not only they check the amount of the transaction being less than the balance Alice has, that is one part of the validation, but the second part of the validation would be that they use Alice's public key to check it is indeed Alice's signature. If it is Alice's signature, then only they declare the transaction as valid. Therefore, the transaction once it is there becomes non-repudiable, because without Alice's private key nobody could have signed for Alice. So, therefore, the signature verification has to be done. Now, if the signature does not check out, so they know Alice's public key and they check and the transaction is saying that oh, it is Alice is paying Bob, but it is signed by somebody else, then we do not have any reason to validate that transaction. So, therefore, nobody should be able to forge signature without Alice's private key, that is the assumption. Now, if Alice's private key gets stolen, then that is a different story, but we assume that Alice's private key is Alice's responsibility. And also, if Alice said that I want to pay 100, but somebody in the middle intercept, see this message is going to the broadcast to the entire blockchain, that is how the blockchain works, everything is sent to everybody. So, if Alice pays Dan, see, let us say somebody changes it to say that Alice pays Dan 200 coins. Now, Alice said 100 coins and he signed the transaction. Remember how they sign the transaction? They basically take the transaction message and then apply the private key and then they encrypt it, right. And this encryption is basically with the private key of Alice. So, with the private key somebody should be able to open it and then they will get the message back, right. So, therefore, if message is forged by somebody, they have to also forge Alice's signature. Otherwise, if the message is changed to message prime, when somebody encrypts it with some other private key, then that will not be able to check out with the Alice's public key, right. So, when you try to decrypt it, it will come out as garbage. So, therefore, if the transaction message comes to with Alice's signature and I am able to decrypt it with Alice's public key, that means the Alice must have not only done the transaction, her transaction amount or any information she has put in the message is also not tampered with, right. So, that basically gives us the not only authenticity, also the integrity of the transaction. So, therefore, now in the ledger we have to not only store the transactions message or the information like who gets how much, we have to also put the digital signature that came with it. So, that later on if I again want to validate all transactions, I should be able to validate it by using the public key of the person who put the transaction in, the sender, and then use that to verify that the transaction amount and the whoever is saying the transaction is from are genuine, right. So, we have to also add the digital signature as part of the transaction information. So, now we have the transaction validity redefined or extended the definition. So, not only the balance on the of the sender should be greater than the amount, also transaction signature validation succeeds. So, the sender's public key should be used to validate the signature and it should succeed. So, now how do we do the signatures in programmatically? So, there is this RSA public key type. So, RSA we talked about the reversed Shamir Edelman. So, here we are assuming that we are going to use RSA public key cryptography, and how a public key is represented is actually there are multiple different ways of representing a public key. Remember, we said that in RSA as an aside in the previous some previous lecture, we said that we take two very large numbers, prime numbers p and q, we compute n is equal to p times q and we compute phi n equals p minus 1 times q minus 1. Then we choose a number and then we choose a number e which is whose GCD with phi n is 1, and then we choose d which is the multiplicative inverse of e modulo phi n, and then we publish e and n as public key and we keep d and n as private key, right. So, in this case the public key is represented by the this is called the exponent and this is the number. So, this is e and n has to be represented, and how do you represent that? You actually do sometimes you do these are very large integers. So, if you represent them in binary and then convert them to hex, or you can represent them to binary and then you can do a base 64 encoding. So, based on that there are many encoding schemes, multiple encoding schemes. So, here we are talking about DER encoding, which is one of the standard encoding of the key. So, the data of the public key will be this information, and then the size of the public key would be the size information. Now, so you have this public key has a verify function, and verify function basically is success when the signature verifies with the public key. So, the public key information is here, the signature information is here, you send it to the verify function, and if it is success, then we say that we have verified that the signature is genuine. So, that is how the signature is going to be represented. Now, the question is where do you get the public key, right. So, you know, in SSH if you have used SSH, then there is a keygen function that allows you to create private key and public key, right. So, when you use a keygen function that you can create your own private key and public key, then you can keep the private key guarded by some passcode, so that nobody else who accesses your computer cannot easily read it unless they know your passcode. The public key you have to publish or you have to upload to, let us say, GitHub or something. So this is how we actually generate the keys, but that is not the point we are discussing here. Generation of the key is not difficult. What we are discussing here is what we discussed in a previously also, which is how do you tell other people what your public key is. Now, in our setting, for example, in this particular example, we can tell the bank our public key and the bank can store them, but the question is, if that happens, then the bank can misuse them, especially if the bank has the private key also. Like if the bank gives us a public key and private key, then bank generated the private key also, and therefore, the bank will know the private key for every public key. So, then bank can actually forge messages, transactions on our behalf, which is not good. So, similarly, if I have a blockchain which is not maintained by a bank, but maintained by, let us say, a whole crowd like of 10,000 people who are all participating in the blockchain, then and I generate my private public key pair, then I can announce that this is my public key. Now, the problem with that is that what if somebody else announces a public key as mine, right. So, that problem is still there. So, in our case, in our single controlled blockchain case, how we solve it here in this example is that instead of bank giving us account number, see right now when you open an account in a bank, bank tells you this is your account number. In this system, what we assume is that I generate my public key, private key pair, keep the private key and hash the public key, right, and send bank the hash and say that this is my public key, this is my, make this my account number. So, the customer is now choosing his account number. Banks may or may not like that, but in this case that since this is a made up bank, we assume that the bank is okay with that. So, bank gets the account number from me, and when I sign transactions with the private key, then my account number can be come handy in very validating that my signature is genuine. So, why do we want to hash? First of all, the public key, if you generate a public key using keygen, you will see that the public key is usually very long string of numbers, and therefore, nobody can remember, or it's going to take like many letters or characters length string to represent the account number. But if you hash it, then you can map it to a fixed length digest, and then you are going to use that maybe 16 or 32 byte digest, and then use that as your account number. So, we will revisit some of the hash function properties, although we have already done this, that the number of real keys, because the keys are of much larger size, if you hash them, many of the keys will become the same hash. The hash function should be such that that should not be common at all, and not only that, people should not be able to find that in case they want to. And so, that is the two properties. One is that hiding property, or what is called, this is the hiding property we talked about before, that given a hash you should not be able to find what the original was. And then collision resistance, that is you cannot create two messages yourself whose hashes are going to be colliding. So, now what you do is that a transaction will have sender's public key, sender's address, receiver address, amount and a digital signature, right. So, the address is the hash of the public key. For receiver, you only need the hash of the public key as the account number, because that is the account number, whereas for the sender you need to also tell the public key, because otherwise how would you use the digital signature. So, these account numbers are also called addresses, in line with how Bitcoin calls them. So, in Bitcoin also the addresses of each person is actually a hash of a public key. So, each person who wants to participate in the Bitcoin ecosystem, they actually create this public private key pair, keep the private key, the public key is hashed, and then that is announced as the address of the account, and that is the also called a wallet, right. So, that is a wallet address. So, public key is included in the transaction, and you can check whether the public key is genuine by checking the sender's address by hashing the public key. So, the question is, and we already discussed this, that why are not we using public keys as addresses, because public keys are too long and too cumbersome to deal with. So, now one problem here that can happen is called a replay attack. So, let us say this sender is sending some 100 amount to this address, and then this sender now out of this 100 sends an amount 50. So, after transaction 1 this address has 100, and then to buy something she uses 50. Now, somebody who is listening to this transaction actually can change this, and for example, this person can broadcast this transaction. See, transactions are broadcast because everybody needs to see all the transactions, because everybody is keeping track of the transactions into blocks and so on. So, this person then broadcast another message with the same with all the same thing, like the public key of this sender, the sender's address, his or her own address, and another 50, and nothing changes because message integrity cannot be sending the same thing again. So, there is no message integrity problem. So, now if others believe that this is another 50 coin transaction, then at the end of that this address will have 0, although she intended to actually spend only 50. So, that is somebody is replaying an old transaction again. So, this is one problem that one has to worry about. So, therefore, what you do is you have to make some tricky solution. So, every time you make a transaction in this kind of setup, you do not keep the balance whatever the rest of the balance in the same account. So, you create another account with a different address, and then the part of the transaction you say that give 50 to this address and give 50 the rest of the other, like in this case 50 to a new address. So, now the original address no longer has 50 left, original address will have 0 left, whereas the receiver of the transaction will get 50 and rest of the 50 will come to my own a different address, what we call an alias address. So, therefore, replaying the transaction will not help, because when somebody tries to replay this transaction, the sending address no longer has any money. So, this is something that is very common, I mean that is done in Bitcoin, that every time you make a transaction, you broadcast the transaction, if it is the full amount, that is you have only 100 and you are giving out 100, then that is fine, then in that case you do not have to do anything. But if you are giving part of the what you have, like in this case 50 out of 100, then the rest 50 has to go to a new address, it cannot remain in the old address because replay attack can happen. So, this is something important to understand. So, one last minor detail, for every transaction we also add the transaction hash. Now, remember the transaction contains the public key, the sender address, the receiver address, the change address, that is the new address to which you want to send the change left after the transaction, and the amount of the transaction, right. So, this is hashed, and then this hash can prove that your transaction is not tampered with, and then you sign the transaction on the transaction hash rather than the entire transaction. Of course, that makes the signing easier, because the entire transaction has a lot of information, and then if you create a digest and then encrypt the digest with your private key, that will be faster. So, therefore, it makes sense also to do the hash before you do the transaction signing. So, the final transaction structure will then be a public key, source address, destination address, change address, amount, transaction hash and transaction signature. Remember that source address is result of a hash. Similarly, destination is also result of a hash and change address is result of a hash. All addresses are hash of the public key, but you also need to give the public key. So, you have to use the public key as a vector, and then at the end you will actually add another vector of the signature of the transaction. So, this is basically, see, it is a sequence of bytes, right, because it is a 8-bit unsigned integer where they are basically bytes. So, you represent the public key as a sequence of bytes. Similarly, you represent the signature also as a sequence of bytes. So, now we have a third definition of transaction validity. First, the transaction hash is there, and then you should be able to verify the signature on the hash, and then your sender's account must have enough balance, right. So, this we already had, and we also had this signature thing, but the new thing is that we have to take the hash of the transaction and then verify the signature on the hash. In the exercise that we are proposing, so we will give you a set of already almost implemented blockchain as per today's discussion. However, there are places where you have to fill the gap, otherwise this will not work. So, there is this function this file called transaction.cpp where you have to implement these checks, right, the checks of the signature verification and check of the balance being enough. So, this is the code for computing hashes. So, this is a little bit hairy, but this is the type of the SHA-256 hashing. So, you initialize it and then you keep adding what is the next piece of data that you want to add into the hash, right. Your data structure has this public key, you have the sender address, you have the receiver address, you have the change address, you have the amount, and you have the signature. Well, signature is not part of the hash. So, what you are doing is that you are telling the size also, and then you are adding one by one and updating the SHA hashing process, and eventually what you get is the transaction hash. Back to the discussion on blockchain again, that verification part is done, the question of permanence. So, now one way to have the permanence is that it is highly tolerant to failure of storage. So, for example, if the transactions are all stored in one central location and that location fails, then you are going to have you have lost the data. But blockchain is one thing that happens is that blockchain is, as I said, is a dynamic structure, it keeps growing, but at any point everybody has a copy of the current blockchain. Now, they may differ slightly from each other because, as I said before, because of network delay and everybody is far from each other. My copy may be slightly behind your copy. I have not gotten the latest block added to my copy yet, but we have an eventual consistency that eventually everybody will have the same blockchain. So, all participants having a copy of it. So, we have the permanence in the sense that if I lose one copy or 3 copies, I still have a lot of copies around. Second is that every transaction is broadcast to everyone, and that is how everybody independently creates the chain, right. So, this is an interesting thing is that nobody is telling them what goes into the blockchain, what is the next block. When a next block is created, multiple people will create next block, and I discussed before that this multiple people created next block is actually going to be slightly different from each other, because the last transactions that they have seen, their choices of transactions that they put into the block, all that stuff will define what each individual creates as block. Then they compete. Once they compete, and then one of them will solve the hash puzzle first, and then he will declare himself winner, and then he will broadcast the block with the proof of his win to everybody. So, everybody is now getting a copy of the block that has won. So, even though I have been sitting there by myself, and I have created my own block also, but unfortunately I did not win. So, once a winner block is broadcast to everybody, everybody adds that copy of that block to the latest blockchain. So, that is how the distributedly eventually everybody has the same chain. Now, there are some race conditions and some periods of time when multiple copies may differ from each other, but we will see when we discuss Bitcoin blockchain that eventually everything becomes convergent again. So, there is a transience that may actually make some difference, but overall it works. But in our case actually that is not a problem, because we have only one copy of the blockchain that is being maintained by our program, but that is not real situation. So, what I described as this block being winning and then broadcast to everybody, this winning process is called a consensus process, and so there has to be a consensus algorithm. So, the hash puzzle solving is the consensus process that is followed by Bitcoin and Ethereum and few other blockchains, Algorand for example, whereas many other blockchains there are other consensus algorithms, and we will see them like Byzantine fault tolerant consensus algorithms of various flavor. So, consensus algorithm is not necessarily always by hash puzzle solving, but the first few blockchains that we will see, that is Ethereum and Bitcoin, we will see that the consensus algorithm is indeed based on hash puzzle solving and therefore based on mining. Now, as this is where we actually are having an advantage in our particular example, programmatic example, is that we are only keeping one block copy of the chain within one program. So, we are able to create like shared pointers which are memory addresses and so on. But in case of real blockchain, we have the copies all across, and they are on different systems. They might be on Linux system, they might be on Windows system and so on. So, therefore, the pointer sizes will be different based on 64-bit machine, 32-bit machine and so on. So, therefore, this kind of pointers are not what is used in the real blockchain. So, the previous pointer actually across different machines work slightly differently. So, the previous pointer in this case refers to the hash of the previous block. So, as I said in the previous lectures also, that is enough actually, if you think about it, that I have many blocks, I have the hash of some block which I consider my previous block. So, all I have to do to check which one is my previous block, I have to go through all the blocks and compute their hashes, and whichever guy's hash matches with the hash that I am carrying as my pointer is my previous block. So, this way I can keep building the previous to previous, previous to previous and so on, and I can actually cache it, right. So, at some point I will not want to, every time I want to find who is my previous block, I do not want to do all the hashing and computation. I might because once the blocks have become permanent, their hashes also become permanent. So, I can actually cache that information. But the point here is that having the hash of a previous block stored inside your block is good enough for finding the previous block, and that is how the chain of blocks happen. And the first block or the genesis block does not point to anybody before it, because there is none before it. In the real blockchain, they are not memory addresses, they are actually hashes, and they are called hash pointers. The last thing, that where do the bitcoins come from, right. So, the bitcoins are created whenever a block is mined, that is, when a block is created, everybody tries to solve the consensus problem, in this case in case of Bitcoin hash puzzle, and then as a reward of the winner, is given some new bitcoins, and that is only way Bitcoin is created. So, the reason why reward is there is that, because otherwise why would I spend my computing resources which requires money to validate transactions, to put them in a block and then solve a hash puzzle to be part of the blockchain. I need some reason to do it. So, there has to be an incentive. So, this incentive or reward actually makes the system keep going, otherwise everybody will stop mining because it is expensive to mine. So, the reward should be also enough, so that the amount of money they spend in paying for electricity bill and paying for the hardware and paying for the cooling of the very large hardware that they use to solve the hash puzzles should be surpassed by the reward. So, the reward should be big enough, and this is called a block reward, right. So, the block reward initially in Bitcoin was 50 Bitcoins, then after 4 years it became 25, and after 4 years it has now become 12.5, and in another couple of years it will become 6.75 and so on, and at the end it will become 0. And the reason is that the Bitcoin ecosystem also has this thing that there will never be more than 21 million Bitcoins unless the Bitcoin changes its strategy and policy and everything. So, and the only way to create Bitcoins is through the block rewards. So, as we if we keep the block reward the same always, then the then you have to pass the 21 million mark. So, therefore, they are tapering it off, it is like kind of like a geometric distribution, so that the eventual sum becomes 21 million. So, then you might ask, why would somebody be interested in doing mining, spending money to do the mining, solving hash puzzles. So, there is something also that every transaction that you make, you also has to give some transaction fee. So, in the beginning the transaction fee was not there, and we have not included in our example here, but if the transaction fee is there, which means that whoever wins the hash puzzle can transfer the transaction fee from each transaction to his account. So, therefore, if there are 1000 transactions in a block and each gives, let us say, some small amount of transaction fees, then together they will become a pretty good amount, and therefore, the miners will still have incentive to gain new Bitcoins through this process, even though the rewards have stopped. So, this is how this thing is planned to happen. So, the final block structure is that you need to add also the reward address, because whenever there is a reward in the block we should know where to send the reward. Rest is the same as before, it is a list of transactions, previous hash, and in our case it is a previous pointer also, because we are doing it inside the program, otherwise that part is not necessary to be there. So, now coming to your optional exercise based on this this particular lecture. So, first of all we will give you a zip file containing the code, and it will have some instructions. You have to actually use Ubuntu Linux to do this. So, if you do not have Ubuntu Linux, you can actually use VirtualBox, which you can download from Oracle, and VirtualBox is actually a virtualization software, and then you can download an Ubuntu Linux, which is free, and then you can have build a virtual machine using VirtualBox, which runs Ubuntu 18.4 or even later, because we will need you to get some of the libraries that are not usually coming with the Linux distribution, and those libraries are working only with the latest Ubuntu, and then you look at the code in this file crypto-test.cpp to see how the various API functions from these libraries that you have to use, for example, for generating keys and for hashing SHA-256 and so on. And then you have to implement this validate function, right. So, the version 3 validate of transaction, and then you have to implement the block validation, that is how to implement the validation of all the transactions by calling this function. Actually, you can validate, and then you can also, there is a performance bug in the code that is given in the update balances function. so that if you can find, then you will have some good exercise in performance debugging. So, for transaction validate, you have to write code for the checking that the send address is the hash of the public key, that is part of the transaction. Also, you have to compute the transaction hash and check that the hash that has been put part of the structure matches, and then you will also have to use this transaction hash and check the signature that is there. So, these are the things that you have to check for validating a transaction, other than the balance check, which actually we are assuming you will do. For block validate, you have to go through the block is a vector of transactions. So, you have to iterate over the vector and apply the transaction validate to each of those, and if any of them return false, then the block is invalid. If all of them returns true, then the block is valid. Then you do update the balances after each valid transaction. So, you can call existing update balances for this. Then you check the block hash, and then you add the block reward to the balances. Whoever in this case whatever the reward address is, you just put it there. In case of a distributed computational situation like in Bitcoin, every person who creates a block puts his own address as the reward address, but eventually only one of them will get reward. Now, in the same zip file you will get a number of test files, number of data files, and if you use them, then you should get the output. So, you should match them against these outputs by doing a comparison of the this file against the output of this running your program on this data, and that will give you a satisfaction of having done it correctly. So, this shows the outline of the classes. So, earlier when we were actually going through this, we had lesser, we only showed the snippets. So, this shows a little more, like this is a block class, whether it is valid or not. After the validation process goes through, it will be set to true or false, and then you have the, remember this is a map, this map is a hash table for balances, and then you have all these functions, like these are constructor functions. This is actually a data item, this is also a data item, which is the set of transactions as a vector. This is the previous hash, the block hash, and then this pointer is there for our program, because our program is based on single process, therefore, we can use real pointers. Transactions are also actually having this structure, and this balance map hash table type is actually defined in this transactions.h, and this is what are the different parts content of the transaction. We already saw, we have to have the public key, the source address, destination address, change address, amount, hash, sign, and whether the transaction is valid. The hash result is the so the crypto.h has the prototypes of the crypto functions and the classes. So, in this case the hash result class is defined here, and it has all the constructors, it has the way to set hash from data, and also it has hash result. This is the ampersand operator overloading, this is the comparison overloading, this is the not equal overloading, this is less overloading. So, these are the kind of things, and this is how you access a particular part of the hash result. So, not all of them are required for this particular program, but this is how the hash result class is defined. So, the first block is also called the Coinbase block. So, Coinbase block can be created using this constructor, and where you say that the previous block points to null and its length is 1, its validity is set to false initially, later on if when it is validated then it will be done, and in the beginning you reset balances. For regular block, initially you create you initialize all these different data items, like the validity is set to false, length is updated to the previous length plus 1, previous hash is the previous block's hash, and previous block is the pointer to the previous, and you reset balances. After that, with different functions you keep adding transactions and so on in the block. So, the steps you need to do is you have to download the latest Ubuntu, and if your machine is not dual booted, install VirtualBox from Oracle and use virtual machine to run Ubuntu. Then you go to you clone the open RESSL library from GitHub, and then you do the installation of the various libraries, boost library, automake, autoconfigure, etc. Once you have installed all this, then there is a readme.md file which you have to view to see how to build and install the portable manager library, and this is the where you get all the crypto functions that are required. And then you download the code for blockchain exercise from the Xiaom platform that we will be putting in there, and follow the readme file within the source directory to build it. And then you write the specific functions that you require in the homework. So, the writing the functions is not a lot of work here, but what is going to happen is that you have to understand the entire code to actually make the changes, small changes, and that is where you will get to see the entire code and understand how it works and so on, which is the goal of this exercise. So, with that this lecture 3 comes to an end. So, next time we will actually look at the first real blockchain, how it is done, its techniques and structure, and how the distributed maintenance of it is done for Bitcoin blockchain, and we will go from there. Thank you.